Okay, so the first part of this question is, does anybody here not know what MVCC is? Or anybody here would like to have it more explained? Okay, no, so we can skip that part. So we have actually a few different implementations of MVCC. So we've got Postgres, Cassandra, InnoDB, which is blog-based. I can also talk a little bit about Couch, although not in any great technical detail. So why don't we each take like 5 minutes to go over that? So Bruce, do you want to start with the portion where we go into our implementation?
Yeah, sure. This is really a two-part talk. The first part talks about how MVCC is implemented in Postgres internally, and the second part talks about how we do cleanup in Postgres. We're going to skip the cleanup part. We're going to skip the cute pictures. Effectively, what we're going to talk about is what is MVCC. We already discussed. We don't need to talk about that. Implementation details and the cleanup stuff we're probably not going to get to. What is MVCC? We talked about that. The big benefit we have to MVCC is readers don't block writers, writers don't block readers, at least in Postgres. That gives us very high concurrency. These databases implement it. These are the best known ones that implement it. This is the way we do it in Postgres. We actually have some visible fields.
Can you go back to the last slide, please?
Yeah. This is not, yeah, I would actually add to this. There's a few I would add to this. Because obviously Couch and Cassandra are not on here.
Yeah, I didn't go kind of the, I didn't do the.
Yeah.
Let's not hold them up to some scholarly standard of research.
Yeah, this is, I think this is off Wikipedia, okay? Yeah, exactly. So effectively the way Postgres does things is we have two fields on every row. One is the creation field and one is the expire field. And effectively those give us the row visibility for MVCC. In fact, they're called xmin and xmax internally. An update is effectively in Postgres, an update is effectively a delete followed by an insert. Okay, I know not all systems do it that way. That's the way Postgres does it. MVCC snapshots are tremendously important because they give you visibility into the database. Here's a slide that basically talks about how we go through the MVCC rules to determine whether a row is visible or invisible. The real takeaway here is that Postgres is storing its row versions within the database, not in some secondary location. I'm not sure I'm going to be able to talk about the cleanup aspects of that, but someday I will. Effectively, here is an example where we've done an insert and we've actually assigned an xmin or a creation ID for that. Okay. Here's a delete. You can see the deletion right here of the xmax, indicating that row is deleted. Here's, we also do row log, let's see here. Multi-statement transactions, we also have a cmin that we use to indicate what transaction within a multi-statement transaction has created that row. I'll do this. Here's kind of an example where you can see we have one row created by one transaction and then 3 rows created by a second transaction. We do some tricky stuff to minimize the storage requirements. Effectively, Postgres uses 3 4-byte fields to handle the visibility rules in MVCC and Postgres. Again, an xmin and xmax, and then we combine the last one into sort of a combination field. I think I have, what, 2 minutes left? 1 minute left? Effectively, cleanup in any database, you're going to have to clean up deleted rows. That's sort of a problem that everyone has. We also are running, in Postgres, we need to clean up rows created by aborted transactions. We also have MVCC cleanup because, again, we keep the old and new versions in the same table. And effectively, we have 2 ways of doing that. One is a per page cleanup, and the second is a bulk operation that happens automatically. The term is kind of vacuum, although again, we use different terms for the two various fields. That's about all I want to talk about. This is kind of pictures of some of the ways in which we recycle stuff while the data is live. We have a free space map that indicates where to put new rows. And that's about, no, still more. This is the handling of updates. We're able to very efficiently do single page cleanups there. And I think more slides. Yes, this is a summary of what it does, clean up, and that's it.
Optimistic or pessimistic commit?
I don't know what that means. What does that mean?
So the general, or excuse me, rollback is what I should have said. It is very inexpensive to roll back in
Very
Postgres.
inexpensive to roll back.
Yes.
In fact, do nothing and it rolls back.
Well, is that really true? Because there's a cleanup cost.
There's a cleanup cost, right? Yeah, that's true. You're going to have to, yeah.
But that's
true.
later on. The
Well,
initial cost of saying, no,
Right.
we're not doing this.
There's an important, but it's an important
Right.
cost when you're.
Oh, yeah.
Right, but there's no additional cost to roll back compared to having issued the statement in the first place.
Whereas in, say, InnoDB, it's significantly more expensive to roll back than commit. Dramatically more.
Yeah, there's no action we have to take specifically. We can do it leisurely at some later time. But the real thing I learned in writing this talk and looking at the whole MVCC behavior, having lived with it for 14 years, is that effectively, even if we didn't have to do MVCC cleanup, which we do, and even if we did, we would still need to do cleanup for deletes, and we'd still need to do cleanup in some sense for aborted transactions. So, you know, it's kind of like, yeah, we got to clean up for MVCC, but effectively, we've got to clean up anyway, even if we didn't have this behavior.
So with the timestamps, if you have, the timestamps don't seem to be well ordered. You could have a transaction which failed. So you, how does the system figure out if a version number is current?
Commit log.
Yeah, we have I didn't include that slide, but we have a bitmap file which indicates which transaction IDs are committed or aborted. That bitmap normally stays in shared memory, so when somebody's looking at a row, they can very easily look up that transaction ID in the bitmap to determine whether that is committed, aborted, or is in progress. Basically, three possible states.
And then after it's looked this up, it writes this out in bits, right?
Yeah, after it's looked up and it's determined it's aborted
So,
or committed, it will write it.
First time after something commits, say you're reading through it, hit bits aren't sent, let me check the commit log. Okay, I know what the state of this is, and now I'm going to write it out in hint bits, and we don't have to reference the commit log at the next time we read it.
Where are the bits
In the row.
in each row?
Yeah,
Yeah.
which is,
Its own problem.
yeah.
So it's a cache for the,
Yeah.
Yeah.
Mm-hmm.
It's its own problem in what way?
Well, so for
Check
example,
something.
you think, yeah, and for example, you've say just loaded a database in from backup, and you think you're loading it in read-only mode, and it's doing all this disk I/O. And the answer is the first time Postgres has seen a page, it sets all the hint bits. And then that dirties pages, which the operating system will flush to disk. So it generates a bunch of extra I/O, among other things. So there's been a lot of discussion
That's
about
at least
Postgres
bounded
doing
by,
that.
that sounds like that's at least bounded by a constant factor, right? It's only twice as much data, is that right, or is it more than?
Well, but I mean, it's an issue for administrators and optimizers if you think you're doing read-only access and the database is actually writing stuff. Do you follow me? So it's also been an issue blocking certain other features like per disk page CRCs, for example, become an issue because these hint bits change all the time. So.
And they're not f-synced down particularly.
They're not wall locked.
Yeah.
Yeah.
Anyway, let's move on to the next implementation. You want to talk about Cassandra?
Sure.
Presumably, Blackboard. It's
So
on your job.
what, I guess, in Cassandra, I mean, so Should I just talk about it on a single node? 'Cause there's also, the whole idea of a cluster, with multi-master, you have to deal with conflict resolution there.
Right, we have a conflict resolution between updates and different nodes. So I guess just deal with the impact of conflict resolution on the MVCC.
Right, so the nice thing with Cassandra, nice and bad thing, you don't have to worry about transactions, that's good. But, so basically there's a read path and a write path, so I'll just go through each of those. So the write path will, what happens, let's say an insert comes in, so Cassandra is running in JVM. There's concurrent hash maps, right? So that's effectively what it's using. So it inserts the write into the concurrent hash map, which is the currency there, and then at the same time it flushes it out to the commit log. Right? And then once this in-memory sorted hash table gets to a certain size, it flushes it out to disk, which gets written out to what's called an SS table. So it's basically like a LSM table that big table defines in its paper. So what happens is over time you get lots of these SS tables built up. And what happens, so for a given SS table, there's three things. There's a Bloom filter. There is a index file. And then there's the actual, the data file. So over time, so what happens is then on the read path, right, it checks on the read side. It goes in, and basically the binary mem tables can be cached, right? So it can keep a certain percentage of data in memory, and you can also cache just the index files. But basically what happens is when you do a read, it checks the cache, any in-memory table. And then if it doesn't get a hit, it checks the Bloom filters. And then after a while, if it gets a hit on one of the Bloom filters, it checks the index file. It finds where in the index file that doesn't store every key, but it stores it's configurable. You can set like every 128th key or every 64 key, however many you want. So it's basically an offset into the file that it seeks to. So what's cool about this is since you can cache the index data, since it's relatively small and cheap, your reads is actually just one disk seek, or none if it's in the cache. But the nice thing is that you potentially only need to do, in theory, the worst case you do two seeks. But since this is so cheap to cache the index data, you can just one seek, which is why so the write path is really, really fast. There's basically there's relatively no CPU overhead, so it's really just as fast as you can write to the commit log. And then on the read path, you're just doing one seek.
On the read path, I thought there was a scenario where you might end up having to read from multiple SS tables.
Right.
Like
So
you're
you're absolutely right. So if the cache, so let's say you've written the data the same key 4 times over the course of however long, and it ends up being in 3 or 4 SS tables, then obviously you need to read those multiple SS tables, figure out which one is the latest. the current version of Cassandra, it sort of punts the conflict resolution to the client, so every insert passes a timestamp. So it's up to the clients to make sure that they keep their timestamps in sync. And the newer versions that are in development are, it's basically a reconciliation class, which could either be a vector clock or you could define your own clock resolution class. But yeah, so the way that we deal with that is in the background there's a compaction process, thread process that's running, and once you hit a certain number of SS tables, it goes through and it compacts them. So that problem of having to read from multiple SS tables is really up to how you use the data. If you're doing lots of updates, then you're going to have more compactions. But if you're writing unique keys, then obviously you don't really have to worry about it. So you can actually turn off compaction in newer versions. So it's really up to your use case, which is kind of the whole idea behind products like Cassandra. It's really just if it works well for your use case. So that's how it works. And then within a cluster, there's lots of resolution techniques to figure out, which one do I want, which one should I write to for eventual consistency? At what kind of eventual consistency do you want? Cassandra gives you the ability to specify, I want it to be completely consistent, or I want it to be, just partially consistent or quorum consistent. But that's the general idea.
Is this well documented in the Cassandra manual?
Manual? You mean the wiki? Yeah, it's on the wiki. There's no book available yet.
There's a Riptano online manual.
Yeah, so I actually work for Riptano.
Yeah, okay.
And so that's the current documentation, probably the best documentation. Yeah.
What use cases is Cassandra optimum for?
Lots of use cases. Obviously I'm a little partial, but it's for there's a list of limitations. I think it's a better way to say when you shouldn't want to use it. Anything that requires transactions, like multiple transactions over a period of time. You don't want to use it. And if you are storing really large amounts of data under a given row, like if you're storing videos,
Yeah,
kind of stuff.
that's a case not to use it.
Yes.
But if you were updating lots of little pieces of information frequently, sounds like that's in its wheelhouse.
Yeah. The difficult part with it is thinking about how to store your data to cover your use case. Because let's say you want to search. Let's say you want to access the data 5 different ways. Let's say you want to access users by their country they live in and by this or by that. You need to think about that up front and build that into your design. It doesn't allow you to once it's live and you have to there's ways to shoot yourself in the foot. You could do it the really slow way, or you could think about it up front and do it the right way. So if you have to do a full row scan of all the rows to find out, to call down the list of people within a certain country, you could do it that way. It's just going to be a big performance hit. So it's better to kind of think about the problem, ahead of time. So I think it requires more design up front.
Okay, and Wikipedia doesn't have a concurrent hash map page. Is there another name I can look that up under?
A concurrent hash?
Yeah.
It's in
Java 6.
No, I found, this Java library.
Yeah.
I was curious.
Yeah, so the newer versions of Java, the concurrency package was updated in Java 6. So you have a concurrent skip list, you have concurrent hash maps, you have concurrent lots of things.
I don't know how a concurrent hash map works, but the skip list uses.
Let's do.
It basically uses the CAS stuff, the copy and swap approach to things.
Concurrent hash map?
I think so. Okay. So, Rob, did you want to go over the InnoDB implementation briefly?
Sure, although,
And then I'll say it's exactly like yours.
What?
okay. Can I change this?
Yeah.
All right. Web browser, web browser, web browser. That's not a web browser that I care about.
You can close it.
How do I get a web
Right
browser?
there.
Sorry.
GoDaddy.
See how many words I spelled. Let's see, do we have it here? No, we don't. Okay, so ignore what's up there. You guys are probably all fairly familiar with how something like the InnoDB MVCC implementation works. So the first time you start up MySQL, you get 3 files. Wow, that's horrible. IB data.
On those railroad charts, draw on the end that's the sharp end, not the end that's rounded.
Okay,
Uh,
because that is horrific. Yeah. Much better.
The rounded end is for your hand.
Okay, they both suck. Anyways, IB data.
It's a professional chalk technology. It's debugging chalk. You will keep going.
All right. So you get IB data file, which holds a bunch of things, including a rollback segment. Let's say you create a table. We do an insert, and a very, very small record of that goes into log file. Eventually, it gets flushed out to the table. Cool. Not interesting. So whenever we run an update, first gets written to a log file. The data gets moved from the table to the rollback segment, and we can have and it can be updated again and again and again within the same transaction, and it'll just be like a linked list inside the rollback segment of all different stuff. The logs are really tiny for what you get out of them, and they get flush disk at every commit. Although that's configurable, you can get an asynchronous commit just like PG. Same deal as PG, reads don't block writes and vice versa. Let's see, what else is interesting?
So one difference is you actually support covering indexes.
Yes, InnoDB does support covering indexes, also has in a buffer on secondary indexes, which, so there's visibility information in the indexes. if I
So
remember correctly.
is that still the case? There's no visibility information in the Postgres
Yeah.
indexes?
Yeah, we're working on covering indexes for 9.1, but it would only work for pages where all of the rows are visible to all transactions. So it's going to be the kind of thing where if your data is fairly static, the covering index will work fine. If you've got a table that's got a lot of updates in it, then the covering index won't be usable.
So is that going to take change the page format?
No.
No?
Because the index is the same, the table is the same. The only change is the visibility map files will be more accurate, or we'll have to introduce it. No, I think the visibility map files will be more accurate. So effectively, when somebody says every row on that page is visible, the index will know that and will be able to look at the index alone without having to reference the table.
Is there any thought to, I remember a couple of years ago, there being some discussion of thick indexes inside of Postgres. Did that idea die on the table?
I haven't heard.
Yeah, well, and actually, let me get to the next implementation, because that's actually exactly what CouchDB implemented, because they don't distinguish between index and table.
Okay.
They don't distinguish between.
In a CouchDB database, there's a single B-tree index. Not that anybody in the room would be familiar with that.
What's a B-tree? No. I couldn't help myself.
Because none of the CouchDB people could make it to this, because apparently last week was this gigantic JavaScript conference in Europe.
It's not gonna work. You know, you don't need.
You can erase the gigantic MVCC.
Oh, that's true.
Use the center one.
Yeah, okay. So,
Also, you can erase the server.
and
You know.
my knowledge of this, oops.
I know, I had the same problem, Josh. It kind of jumped out at me. I was like, what is this?
Yeah, well, it's sticky is the issue.
I know you're like doing it, you're like, whoa!
Yeah.
Exact same thing happened. I felt like an idiot. I feel better.
Terrific. No, right.
I know, exactly.
Yeah, but I don't feel
I
better.
brushed everything off of color 10 minutes ago. I look good now.
Yeah. So, so it was actually, it was fairly interesting. I went to CouchCamp to discuss some of this stuff, because Couch is having difficulty with compaction. So they don't really feel like that problem is solved yet with their implementation. But it's an interesting implementation, because CouchDB is a non-relational database. Basically for in comparison to relational databases, every table is a separate database. So they're not concerned with any concurrency between databases. It's not an issue. So when you have a single CouchDB database, what it really is a big B tree with data stored in the leaf nodes. If people are with me so far. So what we have is we have our head node here, and that points to a couple of middle nodes, and those point to a few leaf nodes here. Those point to some more middle nodes here. Those point to a bunch of leaf nodes here, and the leaf nodes actually have data in them.
It's kind of like ISAM, right? I mean, ISAM is kind of this way. Where you put your data in with the index.
Can you turn off the projector? Because the reflected light makes it difficult to see the
Oh,
black
I don't know how to turn off the projector.
Just unplug my thing, it'll go blue. If you unplug my cord, it'll
Yeah.
go blue.
Okay.
Maybe that's go inside there. Right, you like that.
Section.
Okay.
Is that better?
It'll get
Or
there.
should I move over?
I'll probably turn off in a minute.
Keep going.
Okay. So, so they actually wanted to.
It's
So,
a touch screen.
yeah.
No, it's not there, it's over there.
Yeah, so CouchDB, because they're actually committed to durability and consistency within a database, they actually wanted to do an MVCC implementation for this structure. The way that they actually did this was to implement versioning at each level of the nodes. So for an individual database, they have a serialized transaction ticker, a serialized revision ticker.
Is that for all nodes or for all non-leaf nodes?
For all nodes within an individual Couch database. So when you actually commit a write, it needs to briefly hold a mutex on that revision and on the head node here. At that level, all of the writes are serialized. And then what it does is that, say, the head node was at revision 3. It actually updates the head node. It actually creates a new version of the head node at revision 4. And so this new version of the head node still points to one of the intermediate nodes, but it points, if you had to do a split, it might point to a new intermediate node. because the new intermediate node may point to, it may point to a new leaf node here. And each of these down the line gets an updated version number. So there's some lock contention opportunities here, obviously, because you're going down a tree this way. Since the practice of people who use CouchDB is to use multiple databases to hold stuff, there's less lock contention. Of course, there's no specificity with your databases. But the advantage of this is that if there's something in progress currently that's actually already accessing the data while this updating is going on, it can continue to refer to the old versions of the pages until they're compacted later on. So the big issue that they're having with this is working fine for them. The big issue that they're having with this is that the compaction process requires exclusive locking.
It's incredibly expensive for I/O as well.
It depends.
Yeah.
We do compact, so it looks like they read our code.
Probably.
Yeah, I don't blame them. So we do MVCC at page level, and BerkusDB does this.
Yeah.
And it's almost exactly the same as that, except we can also do live compaction even on sub-ranges of the tree. We can compaction in two ways. Optimizing the tree, in other words, if we get a deep tree and we want to optimize portions of it, we can pull the tree back in, reverse splits, all that fun stuff, and also optimizing in terms of the data layout. We also have a compaction API so that you can then go and compress your data along the tree, or down in the leaf nodes. But this is almost identical to ours. We do latches when we don't need to go exclusive. So we now have a latching and locking parallel.
Brief comment about Couch. You guys didn't hear me say this, but when it went we sent it to a load test environment with a very, very good guy testing it. The email report that we got back was titled, "I killed it." It falls down.
It's not. I mean, Couch is really at this stage meant to be a database for desktops and mobile devices and small applications.
We've got it in product.
Yeah. I mean, if you're like I said, if you ask the Couch guys, they say, "Yeah, I'm hosting this huge multi-tenant environment on Couch." It's like, what are you insane?
Yes.
So we have this in production in EMC frames, and Google accounts globally replicated, and in all sorts of other fun stuff. So it's a little bit more stable than Mongo.
We're sitting on what?
Sorry, than Couch.
Then Couch, right?
Sorry, Couch, not Mongo. Excuse me. I get you guys mixed up.
I just wanted to hear what you were saying.
Yeah. So well, I mean, the thing is, Couch is what less than 2 years. Well, no, 2 years old. Maybe 2. Yeah, Couch is 2 years old at this point.
Right.
So no, not the present code base.
Oh,
He wrote it in Erlang like less than 2 years ago. So
Wait, does Erlang run on a mobile device? Is that,
So Erlang was created by Ericsson to run on their switches.
no, but he was saying that CouchDB's.
yeah.
Yeah, it does.
Yeah.
And at that scale, it might actually work well.
Yeah. So do you have anything to add for BerkeleyDB's implementation? You want to come up here?
I mean, I was sitting up here going, wow, he's drawing BerkeleyDB. So it's pretty much exactly the same. We have, so now we're adding MVCC also to our hash table implementation. So it doesn't work exactly the same. BerkeleyDB is C edition. It's a page-backed database. So we're not SQL. Other people can put that on top of us. But we lock on the pages, and if we have a rewrite lock, and you turn on MVCC, then we'll do exactly what he's diagrammed here. The interesting thing is that you don't have to turn on MVCC for the whole database. You can turn it on per transaction. So you can have one in-flight transaction that's using MVCC, and others that are not, maybe that are using dirty reads and whatever else.
So if you've got some turned on dirty reads, they just look and they just ask, what's the latest revision number that's available?
Yeah,
They use
yeah,
that.
yeah, and if there's a read-write lock issue, then they're, they'll take a snapshot, and,
Yeah.
the read will keep a snapshot, and the write will do the work and keep going.
Is everything atomic?
Yeah, if you'd like it to be. It depends on how you configure it. So each transaction is configurable to the degree of atomacy that you like.
Yeah. Do people actually turn atomicity off?
Yeah,
Huh.
for ridiculous reasons. And then they call us and ask us where their data is, and we tell them it's gone. We have all these wonderful, so you can...
Do you enjoy doing that? You get a kick out of it and say...
No, because the sales guy's sitting there going, he's...
Well, we get the
The problem is that a lot, BerkusDB is so configurable. You can choose to turn off any one of the subsystems, the mocking, the logging, the high availability.
Yeah.
And people will come into a negotiation and not understand this. And they'll go, well, this thing where I take out this feature is less expensive. I'd like that price. We go, well, that's the durability feature. That's the recovery feature. And they go, yeah, our people don't need that. I kind of think you do.
if you're regarding this the individual standardized.
We've had a similar experience.
Yeah, my advice is if you're building these database systems like this, don't give people that much configurability. Don't, because they're going to have negotiation points that they shouldn't have.
Yeah, we've talked to people, we've explained to them, you understand that you need 2 machines for the in-memory database to have any chance of surviving a failure.
Right.
And they say, ah.
So because we use all of this, because all this is recorded in logs, all of the MVC transactions, all this stuff that's going on is recorded in our logs, our write-ahead logs. This also works with high availability. So we do log record shipping, not logical shipping, which is a lot of the high availability solutions you see for SQL solutions. They'll ship, the statement or some other middle layer. Not in BerkusDB. We ship what's happening in the transaction logs, and then actually run the recovery process. The same process that if my process is died.
This sounds a lot like our binary replication,
This is
actually.
Postgres,
Yeah.
Same thing,
Same.
exactly. So we just run replication on the log records that we
We
have.
write logs on the slate.
And guess what? The replication code works really,
What do you
really
know?
well. Yeah. Because we've been doing recovery since day
Yeah,
one. Yeah.
crashing forever, right?
So
Crash
clean-
longer.
It's
yeah,
clean
okay.
code. Yeah. What do you know? Anyway, it's entertaining.
Yeah.
I have a question about all the version systems. What guarantees do the systems need as to update order to hard disk in order to be recoverable?
Fsync doesn't lie.
Yeah.
And the hard drive doesn't lie?
Yeah, you
Yes.
can't trust Fsync.
And the disk is
Fsync
still
works.
You can benchmark.
No, Fsync lies.
So there's a lot of the real
It
answer is
depends on the
that
manufacturer.
if your system
Assumption go right to its disk
Yeah.
cache.
if you believe your operating system and the hardware
assumption is that
is
everything
accurately portraying the data's written, you're
I
fine.
have a slide of that.
That's
It's-
sometimes
yeah,
you can't believe that because of the way the file system code works or because of
Well, you
the
certainly can't over a network file.
Yeah, and the problem is that to
right. So there's
really
network
test
file
something
systems.
like this,
There's how your file system is implemented. There's also your
Yeah, it's
disk,
a little
whether or
hard
not
to
you
write
turned off the right to cache, things like that. But BerkusDB has different configuration parameters to make sure that we turn that off for you to make sure that you're convinced it's working.
Yeah, on Cassandra, you can do a periodic Fsync, a Fsync per write, which is obviously really bad.
Extremely expensive.
Or I think there's another one,
Yeah, batch.
yeah. But I don't know what the difference between that and periodic is.
So in periodic, the things execute immediately. Your data is mutated. And then the log is flushed
Oh, I
every
see.
second.
So
But
it
in
builds
batch,
up.
you collect X number of things or you wait X number of milliseconds. And then you flush it all in disk. in one batch.
Right, but the answer is that if you have a crash,
Yeah.
then whatever's in the pending batch can be lost.
Yeah.
I mean,
But
in
you
your case,
never told
if we're
clients
leaving
you did it.
aside duplicate copies again, but
But you
yeah.
never told the clients you did it and you didn't
Right.
do it, so.
Okay, so you're batching before you send the commit message back.
Yeah, you send
Yeah.
a batch of commit
That's the
messages
difference
out.
between
Yeah.
Once you go
Yeah, we have an option for that in Postgres, and nobody's ever conclusively demonstrated that it's actually a benefit.
Right, I did.
Yeah, you did.
For IGN, remember?
For commit siblings?
A benefit compared to.
We used to run those crazy tests, I
No matter
remember.
what the wall log, it doesn't, don't they all, so you're waiting for Fsync to come back, additional things come in for Fsync, and then you've got 3 things waiting, don't they all get Fsync? at the same time to the wall?
Why? That's the flush, kind of like when you're flushing, you take out the records with it. Yes.
Yeah.
Yeah, but you're-
Doesn't that happen irrespective of the group commits siblings or whatever?
Yeah,
it happens.
Yeah, but it happens.
But-
It happens in a very. I mean, you have to have. That happens at a very high level of activity, but without actually increasing the size of the window, the flushing isn't going to pick up very much.
Okay.
But let me make sure that we're all talking about the same thing, because in DB there are three ways to flush. You've got log records being buffered up in your application space. Then you flush them to the operating system and hope that your process can die, but as long as the operating system survives, they should be flushed.
Okay.
And then there's flushing them all the way to the disk. So
Right.
yeah, all of those are different things, and making sure that the disk is actually writing them.
Yeah, because we're offering both, the trying to increase the size of the batch on a synchronous flush, and also asynchronous flushing, which has the potential for data loss.
So it's worth also mentioning that given that disks themselves can break, if you care about that sort of thing, you need to concern yourself with replication, possibly even exposing that to the application layer. Because like Cassandra and other systems do MongoDB as well. So like, if you want your bytes to survive platter, drive explosions or whatever, you need to make sure that they're on multiple boxes.
So MongoDB and Cassandra have great solutions for that. BerkusDB has our replication.
If you have a
It's not
artificially
Yeah.
created
You can pick how much you want to know.
It's a trade-off, yes.
You can overload, but you can just let us take care of it.
Syncing sort of
You're running in the cloud.
It's actually much better.
But you can't lose
Yeah.
data, then
For myself,
that'd be better.
no group commit or 5.0.
At the same time, I notice SSD don't like batches. They can't
So-
like study flow.
So a little bit
So if you
different
have this
issue
5
is
second
one that I've
batches
been,
coming up, it's like oops.
so a slightly different tack. So I've observed that both InnoDB and Postgres, that basically the MVCC doesn't support, you get varying supports for real serialized transactions. So for example, in InnoDB, you can have serialized transactions, but you sort of don't, as I understand it, but you sort of don't get the MVCC goodness, right? Because you basically have to really acquire locks.
Yep. If I remember correctly.
Pessimistic locks.
Yeah,
And,
I don't run servers like that, but from what I remember, yes.
Yeah.
And-
For Postgres 9.1, we actually currently have a bunch of academic papers published on serialization without pessimistic locking. And we currently have a project to implement that. Although serialization, transaction serialization is actually one of those difficult topics where if you talk about it,
Lunch is already on the floor.
okay, if you talk about different people mean different things by serialization, but in terms of serialized transactions, you can never get absolute serialization without effectively forcing everything through a single process, but you can get serialization that's good enough for anybody's application.
Do you remember who wrote that paper?
I don't, but if you look at,
Was it recently, last 2 years?
Some guy in Australia.
yeah,
Maybe it's Michael Cahill,
I think that patch is going
chief engineer for the county.
Yeah.
It's
oh yeah,
going-
no, it is, because because we're down to working on details.
He's the
But I
guy,
don't pretend to know how it actually works.
he's our lead engineer on BerkusDB, and he put that into BerkusDB.
Okay.
So I thought you were talking about the same thing.
So is this-
because we don't have that problem.
Cross-pollination. I remember.
So you get MVCC goodness, but you don't have to, but you actually,
Yeah.
so you do, is this the
Good
one where
ideas
you,
are good ideas.
where you keep
regardless
track
who wrote
of
them,
the
as long as they're not
anti-dependencies, and if you have two adjacent ones, then you kill the guy?
Yeah.
Yeah.
He did that work and then brought it, and that's why he got promoted to be the lead engineer when Keith Bostic left.
Yeah. So, but briefly before I go up for lunch, one thing I would like to hear for the different implementations, what's the biggest problem you're currently having with MVCC? And how are you working on it? So,
Fragmentation.
okay. I think fragmentation is a bigger problem than cleanup. Okay.
Here is flushing, which is when It's a funny term, but activity will build up. The logs haven't been purged out to disk. This particularly happens when you have very large logs. And then InnoDB says, no loss, we're stopping, we're flushing everything out, and the system blocks the hell out. That kind of sucks.
And for Cassandra?
Compaction.
Yeah.
Multiple table functions.
Yeah, and I can say that for CouchDB, it's definitely compaction, because they haven't implemented the full Berkeley DB thing, and right now they're exclusive locking for compaction.
They have a lot of issues.
Yeah, although unlike some of the new databases, they're actually aware that they have issues.
Yeah, and part of it is Erlang itself, or at least how they're using it.
It's off topic, we'll
Yeah,
discuss
sorry.
that later. Berkeley DB, so what would be your biggest issue with your MVCC implementation?
So when somebody's employing it,
Yeah, or, the biggest issue.
so normally Berkeley DB runs with, well, it depends on whether you're deploying in a large environment or small environment, but the obvious penalty with with MVCC is that you're going to have cache overhead. So some of your cache is going to be less hot because some pages in the cache will be snapshot.
Right.
Right. So that's the biggest issue, is it not overusing it and not blowing out the cache. Right.
What's Postgres issue?
Well, Jignesh was just talking about fragmentation. I mean, I still think that we have an issue with cleanup as well, although it's gotten a lot less than it used to be. Yes.
It's like a universal thing.
Yeah.
InnoDB does not have much of an issue with cleanup.
Yeah, they're paying the cost at commit time rather than waiting for deferred cleanup time.
Yeah, because based on that system, they have to hold that. They can't write any of those pages from the table to disk until they clear that rollback segment.
Yeah.
Which is
Well,
probably
the
why.
rollback statement isn't.
Which is why you're having to hold it when it gets too big, right?
Right.
Well, I'm not going to disagree with you. I don't think I'm understanding what you're saying correctly.
Okay.
What we can talk
The
about.
other issue that I would say for both Oracle and InnoDB is that rollbacks are incredibly expensive.
Yes.
Who's Oracle?
What?
Who's Oracle?
We don't have any Oracle in the room, but I can tell you that from personal experience that rollbacks are very expensive.
Oracle, InnoDB,
It's true,
Oracle,
right, yeah.
Berkeley.
Oh, right, yeah, sorry. Oracle the database, not Oracle the company.
Oh, yeah.
We just brought up something called
Hey, Oracle bought Sun. Sun did support for Postgres, and it's a contract.